requested.
Okay, sir.
Yeah. Okay. So this one is coming from August 2019. Am I correct, Prosper? I mean, portrait?
Yes, sir, you are correct.
Okay, cool. So let's quickly begin. So this is actually part of module 5, but it's also heading into module 6, because sometimes in module 6 they require you to do this particular calculation. It's a very important calculation for you guys to do, and so therefore I highly recommend you get very comfortable with doing this. Okay, and I did post a video regarding this one. I'm not sure if it's the same or similar, but the procedure there should hold water for all. So just by the way, okay, so let me just get into the question. So we have figure 3, shows a bolt-up beam consisting of a channel, a parallel flat I section acting as a simply supported beam. The length of the beam is 1.2 meters with a uniform distributed load of 25 kilonewton per meter applied over full span. Okay, so if I could sketch this beam, right, we're not sure of the supports. And then we have, okay, to this, it says we have a point load of 17 kilonewtons, seems familiar as the previous one, and we have a UDL of 25 kilonewton per meter. Okay, and they do state ignore, right, the weight of the beam. You guys remember last time we included the weight at the second part of the question?
Yes, I think we did that part, yes.
Yeah, so I'm just letting you know. So we don't have to include it, but if you do include it, I believe you know how to include it. Okay. So then they're asking for a few things. In fact, they give us the sections. We have a I section, it's a parallel flange, 25 by 146 by 43 kilogram per meter. We have our channel over there as well. And a 300 by 100 by 46.2 kilogram per meter. And then they want us to do the following calculations. Now they do ask us the bending moment that the beam is subjected to, the position of the x-axis, which is supposed to be also called the centroid, right? I think I'll just say it. Then the bending resistance of the axis, that's the second moment of area, that's the IXX, which is covered in that other video. And then as Porter wanted to also know what is the maximum minimum bending stress about the axis. So we will get to this, but anyway, let me proceed. So 4.1, remember, you have two choices in order to solve this. It's either by first principles, right? And that's by taking by finding reactions, right? And then you must find the shear force and bending moment, right? You guys are aware of that approach, right? And the second one is by calculations, which they nicely do for you. So can someone remind me what is a calculations for a point load at the middle of the beam and a UDL to find the bending moment?
So that's WL over 4 plus WL square over 8.
Exactly, WL squared over 8, right? Again, these are only for when the load is in the middle, right? And the UDL is across the beam. You cannot do it if the UDL is half of the beam or this load is like, you know what I mean, displaced away from the center of the beam. So I want to make you aware of that. So all we do, we plug in those values. That's 17. Our weight has been given as what? I mean, our length is 1.2 divided by 4. We've got 25 times L squared. That's 1.2 squared divided by 8. And then this equals to what? You can just get that value.
You got 9,6
kilonewtons meter, right?
Yeah.
Is that correct, colleagues?
Yes, sir.
Okay. So coming back here, we have MI over stress and Y, right? So we're working with the bending. Remember, this is the main bending thing. We've worked out this, right? And what we actually need to work out is the stress, right? Over there, which is the main thing. We still need to work out I, which is part of the next question. So this will be, I would say, like 4.2. This is 4.3, and that's 4.1, and that's 4.4. I'm actually a big boss by recognizing that's how they're actually working it. That's quite interesting for me to put it like that. I've never done this before. So as you can see, now I'm going to find 4.2, arguably 4.2. So what 4.2 is, if you've done that, that revision I put up, it's basically finding the center of this assembly or bolt up beam, right? So we can't assume the center is exactly there or there or there. You know what I mean? There. We have to actually find the center, considering that we have one element being the I section and then another element being the channel. Okay. So how do we do this? Let me just quickly move. So to find it's actually the Y, that's the horizontal. It's the sum of the areas times the centers divided by so by the total of the area, right? So if you, it's, I don't think call it X bar. And this is a general approach. And so what I mean is that you're going to say area one, whatever we're going to call area one, times from a reference point to its center, area two, which is the next element, each reference from a reference point to its center, divided by area one plus area two, right? So let's quickly do this. And we're going to be working with the steel tables from the, the one that I sent. So let's quickly just get some characteristics here. We're going to call area one the I section. Is that okay? And then this guy will be our channel. Can you guys go to the steel table and get me these values quickly? Area one and area two.
Okay, area for I section
Yes.
is 5,501 times 10 to the negative, times 10 to the power negative 3.
Yeah, meter squared, that's correct.
Then
Area two.
for channel
Yes.
is 5,876 times 10 to the power negative 3. 5,876
5,876
times 10 to the power negative 3.
Okay, cool. So I just want to pause here and ask the other colleagues, do you know how to get those areas?
No, sir.
Excuse me?
No, not at all.
That's quite disappointing because we did it last week.
Yeah, no, I didn't touch strings for a while, so yeah.
Yeah, so you're holding us back basically, right? You must admit.
I am just trying to get ahead with the other subjects, but yes.
But
I am.
But because you know that I love you so much, I will show you regardless. Is
Quick
that
way.
okay? Is that okay?
Thank you, sir.
Oh, no stress, brother. Okay, let's quickly go here. I'm just gonna quickly share my steel tables. And then I'm just gonna show exactly where the area is taken from. And this is a very, very important what's this? Look here, we already have a question right similar to that already. Let's go to the steel tables, which I believe is at the end. Let's go to the bottom. So steel tables will be at the end. We did post it in the group as well, if you recall. Why can I know? Where is this now? Okay, here we go. So these are the steel tables, right? Edward, particularly you. Over here, for the first half, we have all the geometric properties or dimensions of the beam. Are you with me? And then area, we essentially get over here. You see there? And it tells you the unit. So I believe we're looking at a 254 by 146 by 43, if I'm correct. And you notice the area there would be 5.5. Am I right? I think portrait is a different one. Unless it's still the same. Are you with me? That should be at the area. Yeah, okay. By the way, all the other dimensions you will notice dimension, yeah, it would be so I'm not sure what steel table he's using. He must probably share it with us. So I know they're fairly close, but they're not close. Then we're dealing with a parallel channel, PC, right? That's 300 by 100. I believe it's this one. And you notice the area there would be 5.76. Can you see that?
Gotcha.
Got you. Okay, perfect. So we'll be pulling a lot of values from those tables, just by the way. So it's worth your while to get acquainted to it. Okay, so obviously this
So
slide.
sorry, quickly.
The portrait, is it 876 or 786? Just check there.
From my book is 5,876.
876. Let me just confirm it. I'm now with you. I have 576 here.
Yes, sir.
Now
5,876.
It cannot be, man. It can't be 8. Let me check on the other book.
Yes, check from the other book.
This is the Wickens book, eh? The blue one.
Yes, I'm using the old book. So check the
Yeah,
new one.
no, I agree with you. I see it's 5.876, eh? Okay, I see it, yeah. It's fine. I'm gonna use that one.
Okay.
From Wickens. Yes, Edward?
No, sorry, sir. I just wanted to ask, those tables are given in the exam, eh?
That is correct, boss.
Thank you, sir.
Okay. Okay, we're happy with this now. That's from the weekend side. So what we've basically got now is that area, that area, that area, that area. So now we need to get these X bars. So again, what the X bars are, it's essentially from a reference point to that element's particular section. So let me just zoom in here quickly. If I zoom here, what I'm saying, you need to find the center of this particular thing. So we typically we can use the top or the bottom. If you watch that video, I nicely articulate that, I believe. So we're going to be using the bottom as a reference. So what we're going to do is from our reference point, we're going to go from here to each respective center, which is somewhere there. And from that base to this channel's respective center, right? We don't know where it is as yet. So I'm just going to put it here as an arbitrary thing. So I'm going to be clear what the X bar is in that formula is from the reference point to the center of this object, right? The approximated center, and then the center to the channel. Okay. So for the I section, right? For the first element, all we have to basically do is find the height on the steel table and then divide it by 2. Is that okay? Can we find that quickly? Let me just zoom out here. I'm going to fill in some of these values so long. So it's 5.501 times 10 to negative 3. And then we must find the height on the steel table. And then divide it by 2, basically. Yeah. Okay, can we find the height quickly? 5.876. I'm waiting on you guys. It's the complete height divided by 2. Inga, Ngamso, Chad, where's my height? Why are we slowing down? Can we find it height?
It says 300 divided by 2.
Can't be 300, man. It's 256. Check. 254. We're looking at the right thing. Okay, because that's part of the height. And just check again, please. Where's that one?
259.
I'm looking at the book now. 250 what?
259.6 divided by 2.
Yes,
Then
259.6.
Yeah, 259.6. So where do you get 300? So
300 is for the channel.
yeah, okay. So 252 divided by 2, right? Are we happy with this? Are we happy with this value?
Yes, sir.
Okay,
Yes,
perfect.
happy with that.
Yeah, so let's put in the second area. So now this one's a bit of a arguably tricky one. So how do we find this X bar? So how we find this X bar is if I zoom in here, what we're gonna do, we're gonna have to add the whole 256 point whatever that was, right? 259.6. We need to add the thickness of the channel, and then we must find the center of this. Now I'm going to show you something very interesting regarding the center of a channel. So let me just quickly unshare and then go back to the steel table quickly. And once again, I did explain this in that other part. Can we all see the channel? Just confirm for me.
Yes, sir.
Yes,
Yes, sir.
Perfect. So what a Y is, that is the actual center of the thing. So what I'm trying to say is, you see that AY going down there? That's the center. That from the top down is actually the center. So what I'm saying is, obviously, this channel, it's not on the flange attached by the web, I believe. So it's going to be the 259.6 plus the thickness, which is what? 9. Then we must subtract 30.6 or whatever value you have there. Are you guys with me? So that AY for channel tells you exactly where the center of gravity is. Is that clear to you? That's that value. That's why they give it there. You guys with me? Chad, are you with me? Is that you?
Yeah, sort of.
Yeah, so what I'm saying is AOI gives you the center.
But you're just adding
So-
that to the height.
I'm gonna break this quickly now. So anyway, that's that value. So be aware of that what the AOI value means. Okay, so I'm just gonna unshare and share again. Here's my whiteboard again. Okay, it's over here. All right, so I'm gonna paste that over here. I'm gonna move it. Okay, just move it there. And then there's my rotate to zoom out. So what I'm basically saying is, remember we are Where's my rotate? We're locking. It's not locking. Okay. So now there you go. So what I'm saying is, we're adding from the height of the you see the things over here, right? The I-beam, for argument's sake. So we're adding up the 259.6 plus that thickness, right? Then we're subtracting down to find to each center. Are you with me now? So if there's unclarity, you must ask, eh? Don't just take my word for it. So this is 0.2594 plus Porter, what is the thickness?
10.
10, right? So it's a clean 10, that's 0.1, 0.01. Then I'm saying you must minus the AY. And what is it, AY value?
27.
Huh?
It's 27.
27. But I confirm on my side. 27, eh?
Yes, in my book 27.
You know the one that you're using, I think that's a taper channel, man. Yeah. I see. Anyway, I'm just gonna go with that one. Fine. That's 27 now. So what it means is gonna be minus 0.027. Okay. We all understand how I got that value. So what I'm saying is we're coming up all the way till the end of that thing. We're adding the thickness of it's the height of the I-beam, the thickness, and then we're going down. We're minusing that AY to each respective center, basically of the channel over there. Okay, so what you can just do now for me is find that Y bar, the centroid. And if you're unsure, please ask. You're allowed to ask questions. What do I get for that Y bar?
Okay, so
Yeah.
sorry, I'm very behind, so please forgive me. So I just want to make sure. So most of these values, if not all of these values, you got from the tables.
That is correct, Chief.
Okay. And
Yeah.
okay, so it's divided. The first X1, that's
Yeah.
only half of the length.
Yeah, it's not just like that. It's to the centroid of that particular one. We're finding the
Of that-
center. Yeah.
Of that beam. Okay, got
Yeah.
you.
Yeah.
And then 0,027, where did that one come from now?
That's from this over here. That's the AY. So in the channel, they give you the center. Basically, it's also from the table.
Also from the table. I'm just looking for AY here quickly.
Yeah, I just had portrait using the Vikens table. So I think on your one should be 30.6, man.
30.6.
Yeah, the one in the total is 30.6, I believe. You get it?
Okay, I got it.
Yeah, so just be aware that I'm just going with portraits Vikens values compared to the toit one. So the toit one is 30.6 here. Yeah. Am I right? Yeah, it is 30.6. Yeah. Okay. All right. So what is it, Vivo colleagues? Can we please move?
Gotcha.
We need to move. Yeah. If you watch the other module 5 part 2, you'll easily pick up again. Shouldn't be a stress. So what is it, eyeball? Okay. Let's get it to eyeball. I have the memo open up next to me, so I can always just check. Obviously, it'll be slightly different. Should be close enough at least. It is an approximated center after all. Inga, what did you get for that Y ball?
Yeah, still calculating, sir.
Okay. Guys are slow. And remember, you can obviously see roughly where it should be, you know. It can't be 200s. Maybe too far up. Give or take somewhere in the 150, 180 region. Somewhere there. Colleagues, what do we get? Portrait.
It's 188,059. That's in millimeters.
188.059.
059.
That's millimeters, right? Yeah.
Yes.
Okay. So what I mean here, if I zoom my image again, the center of this assembly or bolt-up beam is basically, yeah, this is where the X bar is, the assumed X bar. Let me just reduce the thickness of this thing. It's 188. Yeah. That's the from that bottom 188 point whatever. Okay. So we can all, I hope you guys all got that value. And then let's quickly do, so that's 4.2. 4.3 is the second moment of area. Okay. So the second moment of area, we need to find it for each individual element. So the standard formula is I total, right, will be IXX Again, this is the parallel axis theorem, which is again mentioned, but anyway, h squared. Yeah, this formula, yeah, it's a lot to say here. So we'll be using this formula for both I-beam and channel. Okay, and then basically what we're gonna do is add both of them up, right? So we do one for I-beam, one for channel, and then we add them up. So for the I-beam, so I'm gonna say for element 1, I want us to get the IXX value from the table, okay? For the channel. What is the IXX value? So this is the resistance to bending I was talking about, right? Can you quickly go check for the I-beam? What's IXX? Should be there.
So that's 65.5.
You must give me units, eh?
As where am I now? M to the power 4.
Let me check. Say it again.
65.5.
That's correct. Times 10 to the
Okay.
power negative 6. Yeah, that's correct. But let's get the Wickens value. That's correct, yeah. So by the
Oh,
way,
got
anyone,
it.
the times
Yes,
10 to the
sir.
power negative 6, you'll notice on top there, no?
Yes.
You'll notice, yeah, so it's 65.5 times 10 to the negative 6.
Yeah.
Yeah.
Got you.
Okay. Okay, cool. So let's just get the value from portrait because we're using these tables. But you're on the right track, man.
Yeah, I got 19 days to study the subject
Yeah,
after my
lot.
last exam.
That's a lot of time. You should be all right. I know you pull through. Portrait, let's move, man. We're not even on module 6 yet. I wanted to be
No, I'm
done by
just waiting
7
from
o'clock.
you, sir.
How much?
I'm waiting from you.
Yeah, but what is my IX value from your table?
For channel or I section?
I section, I'm saying.
For
How
I
much
section, that's the one he gave you.
No. Is that correct? Is it the same one? I remember using a different table. That's why.
The Wickens one.
Yes, so for I section, IXX for I section is 65.54 times 10 to the power negative 6.
55.54. Thank you very much. Okay. Please be online all the time. Area 1, we have already, right? Which is 5.50. 1 times 10 negative 3. Okay. Let me have this H value. I'm going to keep it open quickly. So guys, what H is, right? Or H1, if you want to call it. It's what it is. It's the distance from the center of the whole assembly, which is 188, to the centroid of this particular one. Okay. So I'll say that again. What H is the difference or the distance of in relation from this the of the Bota beam centroid to each individual element. So if you can quickly calculate what's half of 259 point, what is it again? 259.2 divided by 2. That value we worked out. The one we had in the previous one. I think it's 129.6, right?
Yes.
Yes. So what I'm saying is, so we take, I'm going to just draw this one. Let me just zoom again. Coming here. So the center to this one was is coming up. The center to the element itself, the first one is 129.2, right? So the distance we need is a distance from here, the blue one, right? So it's basically 188 point something minus the 129.2. Is that clear to everyone? That's what that H value means. So Porter, can you just give me the values again? It's 188.
Which value, sir?
That's the centroid 188. Oh, okay, I have it there. Minus what?
Okay,
0.
188.
Yeah. To 0.129. What was it again? The half of that value. This value.
Me, sir.
I'm saying I want this value.
Oh, that is the Y1.
Yeah. Y1
It's 129.8.
129. 0.8,
comma
just like
8.
this, right? Like
Yeah.
this. Okay. So is everyone with me? What this value actually is here, right? It's the distance from you basically find the distance from the center of the actual element to the center of the whole assembly. That's what the H1 actually is. Anyway, let's quickly just calculate I1, which is just that's the first part. We must still do the channel next. Oh, sorry, this is -6 here. Give me. So just be aware what that H value means, right?
I'm getting 18.73 times 10 to the power 3, -3.
18.74.
74.
It should be a -6 value, no? It's not going to deviate that much. So how much is it?
I'm having a -3.
No, man, it must be. Okay. It's fine. I'll accept it.
Hold on. I think I made a
No,
mistake somewhere.
I remember this is -6. I changed that value, no? This is,
Yes. I think the area I didn't multiply by -3.
yeah. Please make sure.
So now I have 84.21
Yeah.
times 10 to the -6.
Yeah, normally it's the same. Okay. Can we just confirm or corroborate that value? Verify? Should be quick to verify. Just give it a minute, then I'll move on. Chad, did you verify the value?
Yeah, I'm here trying to getting errors on my calculator. I don't know what's happening.
Okay.
But I'm here trying.
Okay. Portrait, what did you get for that one?
So I got a complete one. I didn't like cut like the way how you cutting there.
Oh, okay, it's fine. And then we'll move on to the channel now, right? So this will be
Oh, there
I2.
we go.
You got it. So you're gonna say Ix of the channel. Edwin, can you just pull that on again for us quickly? And this will be H2 squared. Okay. Just get that Ix from the channel. But now, before we do that, right? I want you to be conscious of something. Do you notice for the channel or for both elements, can you see it's Ixx and Iyy? Do you guys see that there? Can you guys see that over here, right?
Yeah.
So the value we must take is not the Ixx, right? From the what is this? From the table, we have to take Iyy because we're bending across that axis, right? So you must be careful of depending on how it's orientated. So what I'm saying is that you're bending across this axis, not that axis. Bending is happening over here, right? So you must just be careful. Okay, I don't know if you guys are with me because the value they give you Ixx is like this, right? That's Ixx, right? That's assuming you're bending that way over. But we're not, our channel is not orientated vertically standing up, it's laying down on its legs, right? The flanges, like that. So it's bending that way over. So that means we must take Iyy. Does everyone get that?
Oh, I
What I
got
mean?
you.
You understand what I'm saying? If you even
So-
look at that thing over there. Yeah.
So if I read the table correctly, that's 5,67 times 10 to the
Okay, so-
negative 6 meters
Okay, let's just,
cubed.
I'll write that down quickly. 5 comma.
67 times
Okay.
10 to the negative 6.
Let me write it down quickly. Yeah.
But
5,67.
That's my
Yeah, I
table.
think you're right. Yeah, I think you're right. Yeah.
Well, on my table, which I've noticed is the same as, I think it was Edwin's. It's 4,931.
No,
The
man, it can't be
IY
too far
ones.
off, man. It can't be too far off. Remember what I said? You're not taking IYY. I mean, not taking IXX.
Yes,
It shows the right
Yeah.
one, huh?
yeah, the
Right.
IYY, it's 4,931.
I'm looking. You're saying yours is the same as Portrait's one, or
Yeah, I think
Edwin?
it's the same as Edwin's one.
Yeah, it's 4.93. I see. Yeah.
Yes.
Edwin, can you please check what value did you take there? It's 4.931. Yeah. Yeah. Let me just check another book.
I'm fine.
Just check.
Now I'm not with you where you got that 4.93. Yeah, no, I'm not with you.
No,
Then
no,
I'm
no,
just-
no, no. I see. Yeah, you're right. It is 6.7. You're correct. On the toy textbook. Yeah, you're right.
On the one on the textbook that you showed in this
Yeah,
class.
yeah. No,
That's
it is
where I'm
5.
looking.
Yeah, no, it's correct. It is correct. Don't worry. You're right. You're
Okay.
right.
Fuck it. Okay, sorry. Yes.
Yeah, no, it's all right. Don't worry. I'm looking
Thank
now
you.
and I'm seeing a different values. So Portrait's value on the Wickens textbook, it is 4.9931. I don't trust this Wickens one too much, but let me just quickly have a look here. It should be they have a completely different value there anyway. You know what I mean? I'm just looking here. 300 by 100, I see it's 4.931. This memo, oh man, what's going on here? Okay. For me, I'm pretty sure that it's 5 point, but I mean, I'm looking from this textbooks on the weekends, eh? It's going to be 4.931. Okay. I think I know what the problem actually is. Yeah.
So, sir, let me just
Yeah.
ask you this question. So we follow the tables that's given in the exam. Doesn't matter if we know the numbers or not. You follow
That is
that.
correct.
That's table.
Yeah.
So that might be the weekends that they used in that year, or they might be the book, the one that you showed earlier on. So we use
Yeah.
those tables.
Exactly. This weekend's one is a bit suspect, but I think the values they're giving here is for a tapered flat channel, man. I'm looking at the thing of itself, but anyway.
I got
So
you.
I'm just gonna go with the weekend's textbook now. Is that fine?
That's
4.93.
fine.
Yeah.
Okay, if we go with the weekend, then also, because I notice sometimes the areas are not the same and also the heights. So maybe I would suggest if we can use one table for all the values.
931.
Yeah, but we are using one table for all the values. That's what I'm assuming. The weekend's one.
Okay, no
Which I'm-
problem.
Yeah, you understand. That's what I'm saying. That's why I adjusted this value now. The 4.931 to your one. You see?
4.931. Yeah, I also
Yeah.
get that.
Yeah, that's
But I
from
see,
the old
but
one.
I see what you're saying with the weekends, the shape on top, it looks like have a taper.
A tape,
Yeah.
exactly.
Okay.
That's doing that. Okay, cool. But I think the concept is being brought out, or the approach rather. Let me just put that. Okay. So now we must find H2. And like I said to you, it's from the center of this one, of the individual element to the whole assembly. So we know that this one center, right, is, let me just remove everything here. It's going to be easier first. We know that, just zoom in a bit more. Choose maybe red. We know from here, what is the distance? Okay, from here to here, it's roughly 188 point something, right? I just can't get to this value every time. 188.059. So now we must come from here to this one center. Now this one center, can someone give me that value here? This value over here. This one over here. this actual value here. You see this value here? The 259 plus the 0.1 minus that one. This value. I'm looking for this value. But remember, I don't give that thing center from the bottom. So we're going to find that value on top here. Let me just make this green. So I'm going to come this side from the bottom. It's obviously somewhere here. So all we're going to have to do is just say the green one minus the red one, and then we can get the blue one, which is we require basically the blue one over here. I just need that value from this. I'm assuming you're writing down this one here. Inge, can you perhaps quickly provide us that value?
Okay.
That value, sir, was 242.6. That's in millimeters.
Okay, 242.6, right? So that's 242.6. And remember, we're coming from the bottom. You can do the calculations from the top. But anyway, so it's 242.6. And what I'm saying is, remember, we're coming from the centroid of the channel to this one. So all we have to do is say 242.6 minus 188.005. Are you guys with me? So you can look at it two ways, from the center of the element to the distance, the difference between the two. So it's going to be 246.6. What's that one? 0.246.6. 0.246. What's a 2? I can't remember now. 0.188. 059 squared. This must be squared. 246 point. What was it again? 246?
242.6.
242.6. Okay. 242. Okay. So again, this distance from center of element to center of assembly. I don't know if it helps. Okay, can we get it I2? And all we have to do in the end is say the total IXX is basically the sum of I1 and I2. You just have to add them up. Yeah, thinking, yeah, okay, anyway.
Wait. So IXS is I total. Is het nou reg as ek dit so sê?
Can I say IXX total? No? Can I just be more? It's a total second moment of area, man.
Yeah. So
Okay,
if you go up,
can I just call it, okay, let me just call it I total. No, is it fine? No, it's gonna be just easy. But it's also IXX, which is bending across the x-axis, man. That's fine.
I hear you, sir. But just go up a little bit to the
No
original
problem.
formula. Okay. I2 formula is IXX plus
Same
area
formula.
2, I2.
Same-
It's the same formula. We're
same
just adding
formula.
the two.
Exactly.
I got you.
Yeah. So I did mention the general formula over here. I think I mentioned
Yeah.
it. Yeah, I said it's the same thing, but we do it twice. Yeah.
Yes, just using the different values from the different tables. Got you.
Exactly. Yeah. By the way, this is a very realistic design procedure. Yeah, I just thought it would be nice to explain each concept individually, but I mean, here we are. So can I just get it I2 quickly so we all can just see?
I'm getting 22.41 times 10 to the negative 6.
Yeah, just make sure. Thank you, Chief. Make sure
Yeah,
you always
also
have
got
it
that-
like this. Yeah. So obviously all you do now, you add the two together. Just make sure you always have times 10 to negative 6. That's a standard for what is this? For second moment of area.
Okay, and
88 plus 22, give or take, you can already figure out what it is there.
106.62.
Yeah, 106.62 times 10 to negative 6 negative. Okay, we've achieved the objective there. Nemo has 182, but that's perfectly fine. Yeah, there is some differences. Don't trust it Memo fully, but anyway, did notice some errors. So
So
they're clear to
sorry,
everyone now. Yeah.
sorry. That's 88.21 plus 22.441. Was it correct?
Yeah, from that,
Good.
yeah, that's correct.
Indeed.
Yeah.
Okay, so isn't that 110?
So again?
Isn't that 110?
Yeah, that's what I was saying. I mean, why?
0.62?
I don't know where you get 166 from. Yeah. So I'm gonna do it quickly. 88.21.
Isn't it 84 there on top?
Okay,
Oh,
yeah.
84.
Yeah.
My bad, my bad.
If it's
Oh,
84, that's a different story. Yeah.
Yeah, then it's 106.
oh, okay, it's me.
That's
It's me. It's me.
106, yes.
You must remove my qualifications. So it's 106 point what?
You can give it to
Point-
me, so it's fine.
Yeah,
106
bro.
point.
Pause it, yeah.
Yeah.
Yeah,
What is
point
it?
why?
106.62.
Anybody have connections? Just
Okay. Are we happy with this? Okay.
Yes, sir.
Let's quick,
yes.
yeah, let's quickly move on to 4.3. So 4.3, I mean 4.4, we're just basically using our I like this, and our stress and Y. Okay, so they do ask us, let me just quickly recap the question. The maximum and minimum bending stress about the XX axis, right though, going back. Now what it basically is, if I draw my thing here for you, it's quite simple. We have 188. So there's two distances here. Let me just rather do this rather. So that's the what my Chinese I-beam. And then let me just do it like this. That's the one. So from the bottom, we found that to be 188 059.059. And then can you just give me the distance here from the top going right down? So it's basically the total length divided by 188.509. So it's at 25 something plus the channel thickness coming down. That's where we need to maximum, because this is the central is the neutral axis, basically, where there's no stress. So what I'm saying is that 2594 plus 0.01, and just subtract the 180. You know what I mean? Let me just draw maybe something else here quickly. The total distance here is at which is going to be obviously the I-beam plus the thickness, which was 2594 259.4 plus the 10. So what I'm saying, I want the difference between that total minus this to get that piece over here. Walter, are you with me?
Yes, sir.
Okay. So what do I get there? It's the 260 minus 188. I calculate that. Plus 10. Hey. And then I'm going to minus 188.08059. You should get 81.341. Am I right? 81 point what was it again? 81.349, right? So that and that should total that over there. Colleagues, are you with me?
How much are you getting, sir?
81.8349.
Okay,
It's
I'm getting
81.5.
81.5.
Okay, 269.4 minus 188.059. 81.341. 341.
Okay.
Yeah, your channel thickness is 10 moles. What's the problem? And if you add this two, you should get. Am I missing something here? Do you guys get the 269? Yeah. If you add this two, you should get the total height. What is the problem? Okay, anyway. So there's gonna be two stress values you have to work out. So you're gonna say M, right? So you keep the same bending moment over I, you times by Y, the Y's will be different and you have stress, right? So the moment was 9.6 kilonewton. Our total was 106.62 times 10 to the negative 6. And then we are timesing by these distances. So the first distance is going to be 81.341 times 10 to the negative 3. That's in meters. And we're going to basically see what is our maximum and minimum stress. And then the next value is going to be still 9.6 times 10 to the power 3 divided by 106.62 times 10 to the negative 6 times that 188 now. Okay, are you guys happy with this? Remember this distribution. On top it should be compression, right? You guys remember this thing? You guys remember that thing? Compressed, tensile at the bottom. You guys with me? Remember that thing? The stresses.
Yes, sir.
Yeah, but the difference is now is that because the object is not basically symmetrical, the shape won't be even distributed. So you're going to find more stress where, I'm not going to tell you exactly where, either the top or the bottom. And yeah, that'll obviously influence our design. You're going to find out that the bottom side will have more stress than the top, basically. Okay, so can I get my stress values quickly? Remember the GCC Owens and Nangamso.
Two, three, 4, 5, 6. I got 7.365 MPa.
7.43, the first one, right?
Yeah, first one.
Second one, you can just change the value in the calculator. Our values are not the same as the book, definitely. It's very different. Or the memo, sorry.
Oh, and that's pretty scary.
No, it's not scary. The memo's wrong. That's what's scary.
Look here, I wanted to ask you.
Whoa, I'm realizing something now. Just give me a second. Why is my Y-min 259.6? Okay, I see what they did there. Which is not actually correct, but anyway, yeah, yes, Chad, talk to me.
Okay, second one 17.02
Yeah.
MPa.
17.02 MPa. Yeah. Yes, what you want to ask me?
I wanted to ask with regard to that post that you posted, man.
I have no information on the post. I just thought I'd share.
Oh, okay, cool. I thought it was perhaps something that's at your work or whatever. You had more info on it.
Yeah, no, it's I'm normally on LinkedIn, man. And so then I saw it there. I was looking for something. So I just thought I'll share, you know what I mean?
Okay, cool, sweet. Appreciate that.
Yeah, but you guys should actually go LinkedIn a lot. I don't know where you guys get jobs, but that's the best way
I'm on there,
nowadays.
bro. I'm on there.
Yeah.
Must actually give you a handle.
Cool. Perfect. So when I'm looking at the memo, right, I'm assuming Chad is correct. I don't agree with the answers here because they don't account for what they are doing here, what pasted here. They don't include the 10. You see what I'm saying to you? That 10 of the thickness. So
That's the question
that-
I asked you yesterday. That one.
yeah, and that is not correct because you have to include, because that is completely at the top. There's no way what this actually is, you find the stress under, just at the I-beam, unless, and they're not asking, and they're not even asking at the I-beam. This is the totality. So mine is definitely correct. I'm 100% sure. I can put $1 million on this. How confident I am. So what I'm saying is, the bottom section, if I draw the distribution for this for you. Yeah, I mean, I don't want to talk too much about the college and how the owners are doing stuff, but anyway, so the neutral axis, right, is the 188. And then we find our stress is way more at the bottom, which is going to be in tension, I believe, right? So this triangle should be very big compared to the one here on top, like this, something like this. I could sketch this a bit more better. Bring that line down. So like this, something like that. Okay. No, I don't know, go for you. So what I'm saying is over here, at the bottom, we have 17.02 megapascals in tension. And at the top is going to be only 7.45 megapascals in compression. You guys with me? So what I'm saying, that value they got was just below this here. Is there any question, colleagues, before I move on? Any questions, please, please.
Are you done with the
Don't
whole
breathe.
question, sir?
Yeah, we finished. There's nothing more.
Okay, so which one is the maximum stress and minimum stress?
Yeah, you can see, brother. One is 7.4, one is 7.2. Which one is minimum? This one. Are you with me?
Oh, okay, I see.
Yes, 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 yes.
So basically what you do, you just choose the bigger value is the maximum. You don't use
That
to
is
say.
correct.
Okay.
That is correct. There's nothing more, nothing less. I just want to show you something as well. Okay, but anyway, let me just quickly show you. Is there any questions with this one?
Oh, bro.
It's too much.
Let me just ask this. If you
100%.
go maybe to 4.2, where we calculated Y bar.
No problem. Yep.
Yes, so that formula, the Y bar formula.
Yes.
I see it says the sum of area and the X bar.
Yes.
From the recording that you sent on the group, I see it says Y bar instead of X bar. So I don't know, I'm having a confusion there.
Oh, okay. Just use, you can use Y. It's fine. Yeah. Yeah. You know what I mean? Let me not. I'm altering the convention. You can use Y. Yeah. No, man. I think, whoa. No, it is X bar. I'm correct in the previous one. Incorrect in the previous one. Because for your X bar, you need your Y values. You understand what I'm saying to you?
Okay.
Time.
Yeah. Thank you for making me aware of that. Yeah.
All right. Thank you, sir.
Yeah. I must actually check it out. I mean, I could be suspect here, but I'm just, but yeah. But don't get confused. I mean, it's just the distances, man. I must look again. Yeah. Then I just want to show you this image quickly. Then I want to move. I think we must just take a 5-minute break here. This question took too much time. Portrait. I wasn't planning to do
I'm
this,
sorry.
but it's fine, man.
Actually, myself, what I wanted was only the last part. That's what I wanted.
Oh, okay. Yeah, what I mean, I figured not everyone else did it, man, you know?
So we're gonna
So-
go on with columns and struts. Oh,
Yeah, we have to. Okay, so I'm going to show you this one image, and then we can just take a 5-minute breather. Then I'm gonna make another recording, stop the record, and then I can just start on module 6. So I'm gonna post this image quickly for you. I did post it on the group. Just an example of, you know, what a point load could be. Are you with me on a beam? And what a UDL might look like.
okay, I see.
Yeah, I knew Chad like, I see. I thought so. You see? So don't think these things are theoretical concepts. They're actually very practical. Just that they must be articulated right. Obviously, there isn't time for me to show you too many stuff. I'll show you one more thing before we go on our small tea break. What you'll notice is where they tend to join beams. They're very careful on where they join beams, particularly even over here. And they typically, when they do the design as close as possible, depending on what's happening, they want to join it close to the neutral axis of the beam. But if they don't do it, then they have to size bolts differently, all of that kind of thing. So if you look at these beams, I can just come over here. What they try to do is put it where it's close to possible to the center, if I could use that word, you know what I mean? To the centroid of the beam. That's the logic behind it, because there's no stress acting there. I could show you a few, but that's the basic idea. But it's depending on the connections of what's happening. I want to show you some of this. I never use this one, but this is so software basically to do such design as well. I mean, obviously, this is what so-called engineers do, or what we do. But yeah, just wanted to show you that these things are you know what I mean? They're there. Sometimes we don't get to actually see them in actions or done before the time. Just like another quick image. And also there's a whole module, right, on bolt design and whole standards based on that. On how to actually design bolts, to put bolts, what is the correct size bolts, because bolts experience tension, they experience shear, and the bearing or crushing stress. Just as a quick, you know what I mean? But a guy in civil, in the steel, if you do structural design, this is what they really focus on. But as engineers, we also have to build structures for our whatever, you know what I mean? So this is just a quick one. Okay, guys, can we just take a quick breather? Then can we come back? Is it okay?
Yeah, it's okay. Let me just ask you, have you seen this application with regards to bolts already? When they will like stretch the bolt?
I
and then
actually